Today we're starting section 9.4, which is going to focus on something very similar to the arithmetic sequences we've been doing, but it's going to be called an arithmetic series. The idea of an arithmetic series is that instead of just having that pattern of numbers going from one term to the next, now we're going to be adding up all of those terms. And the way we do that is by using a special formula for either an arithmetic or a geometric one. Some of the applications of this, you could do something for predicting population growth. So you could say, like, what's the average number of children each couple is going to have, or each family is going to have. And then you could use that to predict 5 generations down, how many people do you expect there to be. You could also use this to find the capacity of something like a movie theater, where the number of seats in each row often gets larger as you go back in the theater. There are usually more seats in the back rows than in the front rows. So here's the rule trying to distinguish between the difference of a sequence and a series. So a sequence is just the listing of those terms, and we'll use those more when we're trying to do something like what is the 37th term or what is the 15th term, and that would be finding the number of seats in a specific row of the theater. The series, however, is going to be all of those terms added up, so it's going to be more useful for finding how many people can sit in the entire theater altogether. Here's the formula for an arithmetic series. We'll do a different formula for geometric series later. So it's actually very similar to what you would see for averaging two things. You take the very first term and you take the very last term and you add them up and cut it in half. So a sub n is going to refer to the last term in the sequence because maybe n is going to be 10, in which case the 10th row is the last row, or maybe n will be 20, in which case it's the 20th row. So that'll change from question to question. But a sub 1 always refers to the first term in the sequence. So average the first and the last terms, cut it in half, and then multiply by how many terms you had altogether. In this example, we know what a sub 1 is equal to, and we know what a sub n is equal to, but I don't actually know how many numbers there are here altogether yet. So sometimes you're going to need to use the explicit rule to find the missing piece of information. Sometimes what you'll be missing is what the last term is. Sometimes it's going to be how many numbers you have, and very rarely it might even be finding a sub 1. So using the formulas we used in section 9.3 for an explicit formula for an arithmetic sequence, I'm going to have that a sub n, which I know is 18, equals a sub 1 plus n minus 1 times the difference. Now the difference I can also figure out by looking at the terms in the sequence itself. So if I pick this term, for example, I see that it's subtracting 5 to go to the next term. Same thing from 63 to 58. So the pattern for these, the d value, appears to be negative 5. So that's what I'm going to plug in for d. So I just need to solve this equation for n, because that's the only variable I have in there. So if I subtract 73 from both sides, and then divide both sides by negative 5, and finally add 1, now I know that there were 12 terms in this sequence. And I also could have found that by sitting there and saying 58 minus 5 more, minus 5 more, 5, minus 5 more, 5, minus 5 more. And you could have done that and then counted up how many you have. But a lot of times, especially when there are a lot of terms in the sequence, you're going to find yourself much better off using the formula here. Okay, so now we know the pieces of information we need to find the series, the sum of all those terms. So looking back at our formula, it's a sub 1 plus a sub n. So 73 plus 18 divided by 2, because it's the average of those things, times how many numbers we have. That's what will equal our s sub n. So if I simplify this a little bit, 73 plus 18 is going to be 91. Now, as a tip, rather than taking 91 and cutting it in half, it would actually be easier to take the 12 and cut it in half, because I have 12 times 91 divided by 2. So the order that I do those things in actually doesn't matter in this case. So 12 divided by 2 is 6. And then multiplying by 91 is going to give me 546. So that is the sum of all of those numbers. Now you could also find that answer by just sitting there with your calculator and adding up 73 plus 68 plus 63 plus 58. But again, a lot of times the formulas are going to be much faster and easier for doing this, especially because the early examples we're doing here, we're only giving you like 12 numbers to work with. But later on, you might have to add 30 or 40, 50 numbers, and it's just too easy to make a mistake plugging things into your calculator when you do that many entries. This is a similar example, but this time you'll see that they gave a slightly different starting information. So now I know what a sub 1 equals, and I know what n equals. They've given that to us here. I can also figure out that d, in this case, is 4. However, I don't know what the last term in the sequence is. I don't know a sub n. So again, I'm going to use the explicit rule for an arithmetic sequence. And a sub n equals a sub 1 plus n minus 1. I'm just going to go ahead and evaluate since it's n minus 1. 8 minus 1 is 7 times the difference. Well, 7 times 4 is 28, plus 5 is 33. So now we know what the 8th term in the pattern is going to be. It was going to be 33. So this should be enough information for us to find s sub n. The n value they gave us is 8. The first term and the last term get added up and then cut in half. So to compute this, 5 plus 33 is 38, all over 2. And now in this case, it doesn't really matter which number I cut in half. I could cut the 8 in half, or I could cut the 38 in half. Either way, the answer is going to be the same. So I'm going to do this as 8 times 19. But if you had found 4 times 38 instead, it's going to be the same answer. And then 8 times 19 is 152. So adding all of the numbers up, 5 plus 9 plus 13 plus 17, 21, etc., you're going to get 152 for the sum of this series. So that's all for the notes today. Thank you.